So this is our fourth lecture, and from today we will look into the design of the Francis runner blades. We had only looked into the main dimensions earlier on. So in this lecture today, we will be talking about the axial view of the runner blades. So this will look something like this. This is also called as the meridional view, and we'll also look into the radial view. So this is how the runner will look like when we see it from the top. With these two views, we will be able to make the three-dimensional shape of the runner blades. The things that I will discuss will be explicitly applicable for high head Francis turbines only. This is a short recap of what we saw last time. We now can calculate the values of diameters at the inlet and outlet, and also the inlet diameters, inlet height, sorry, B1. And similarly, we can also now get the velocity profiles at the inlet and the outlet of the runner. So this is where we left last time by calculating these parameters. This is the overall process. Today we will only see these first three steps. We will see axial view, we will see radial view, and we will see how the 3D view of the blades can be made. So first thing is that we start with the runner axial view, and for that we have to get the first streamline. This means that we have to get the curve of either hub or shroud to start with. And how we assume in the case of the high head kind of the Francis turbine is that we assume the hub curve or the shroud curve to be taking the shape of circle or ellipse. This means that we could have a shape like this. We could have a shape like a circle, perfect circle. We could also have a shape like this. So in this case, we have major axis and the minor axis represented by A and B respectively. So in this case, we just have the same value. So this is equal to R basically. And in the case of the ellipse also, this kind of the ellipse as well, in this case, A is greater than B. So we could take any of these options. So we can start with some ratio of A by B. We will see later on that in our case, we take B to be 4 times that of A, or we can take other values as well if we are not satisfied with the shape later on. And we can also start from hub and then move on to shroud. This means that we can first start from the top surface, this one, and then we can develop other streamlines and then go towards the shroud direction. This is the first method. The second method is that you can start from shroud. You can start from here, and instead of going from top to bottom, you go from bottom to top. In this case, we will start with the shroud and then we go upwards. So after the first streamline is defined, another thing that you need to choose is the number of the streamlines. So how many numbers of the streamlines you want to make? So more streamlines you make, more resolutions you will get. It will also increase the computational time later on. For example, if you are having 100 points in one streamline like this, these are the number of the points per streamlines, and then you choose to have 10 number of streamlines, then you will get a matrix later on in the range of 100 times 10. So 100 is representing the number of the points per streamline and 10 is representing the number of the streamlines. So you will get in total 1000 points for this axial view. the output of our program should be that you will get profiles. So for example, you will get profile 1, where you will have the first line, and then in the first profile you will have 100 points if you take 100 points per streamline. Similarly, in the profile 2 you will have 100 points. So in the case where you choose the number of the streamlines to be 10, then you will get up to profile 10. So there will be several points, and you can plot that point in any 3D softwares in order to draw the shape of the blades, or you can also export it in the curve format. So this will be imported in ANSYS CFX TurboGrid mode, and then you can do further CFD. We assume equal flow per streamline. So this means that if you have divided, for example, this is your hub and the shroud curve, and now what you do is that you divide it to 10 points, for example, then each of this small value here, each of these small height here, this is representing total B1 divided by 10 if you are talking about 10 segments. So we will assume that there will be equal flow rate. So if the total flow rate is Q, then you also assume that in one segment there will be the flow rate of Q by 10. For the endpoints, we use the assumption that the flow through the runner accelerates. So we have this equation from our earlier lectures. We know that this is representing B1, and we have, for example, this is the radius, then this is representing D2. Right, so we got this relation from our previous lectures. So this means that area of the inlet is pi d1b, whereas area of the outlet, this 1.1 is representing the acceleration in this case, and area of the outlet is pi d2 square divided by 4, right? So in that case, we will get pi cancel out, and B will be equal to 1.1 D2 square divided by 4 D1. So this means that B will be much less than D2, right? Or B is less than R2 as well. So what I'm trying to say from these relation is that when you draw a streamline, although it seems that in the inlet the height is small compared to the passage at the outlet. So if you compare B1 and D2, you can see that D2 is obviously greater than B1, but the area actually at the inlet should be higher. So although B1 is less than D2, we will have area of the inlet always greater than area of the outlet. So in the streamlines, don't get confused when you see that the height is small compared to the total spacing at the outlet. So we will see these streamlines in the coming slides. And after we have the endpoints, this means that in the case of the ellipse, for example, this is our ellipse, then we'll have to cut it somewhere. I will also show you the code later on. So we'll have to cut it somewhere, and then we will have our curve of the shroud. And after we have this curve, we can develop other curves as well just by integrating these curves together. So here it is representing one of the ways how we can do that. Draw a line between these 2 points, and then what we will do is that we will draw a straight line normal to this line, and then based on the height, because we know now the height of each of the segments, then we can just keep on integrating it until we will have the complete points. And then we will also need some of the other formula in order to plot this. So first we will need the angle. Here the angle is represented by these points RZ, Ri minus 1 comma 1, Z I minus 1 comma 1. So this is our point of interest, and this is representing the successive and the preceding points relative to the point of interest. And we can draw a line like this. So alpha is representing the angle made by this line with the horizontal line. We can also get the value of the Ri comma 1. So Ri comma 1, here there will be Bi comma 1, and between Ri1 and Ri2. So this means that in this point we can consider the radius to be Ri1, right? So these are all mathematical. So runner can be represented by several curves like this, for example. So this can be represented by small cylinders. You can just think that this is a small cylinder, and then there is another cylinder which has the radius a bit smaller, and then there can be another cylinder. So there can be several of these small cylinders, and finally you get the shape of the runner. So for each cylinder there will be this height of B, right? Bi comma Z. So for each cylinder you can get this height, right? And then for each cylinder there will be the radius of R. So that is why for each cylinder you can get the area of 2 pi R B. And similarly, what is B? You can also get it easily by using the triangle law, the right angle law. So simply Bi1, the height will be equal to Ri2 minus Ri1 divided by sine alpha. So this means that when you put it in the code, you have to follow this principle and do it for all the streamlines, all the points. And after that, we just use the known terms. We just rearrange it to get the value of the successive Ri and Zi. So now we will get another point which lies close to Ri1 and Zi1. Here, one thing that we need to notice is that here this value R1 plus, here what we have done is that we have created an ellipse which has the origin here, and then we made a curve, a shroud curve here, right? But in reality, what happens is that you need to translate this curve into the center of the runner. So this actually is not the center of the runner. So you will need to transform it or translate it to the center of the runner. So what is the center of the runner? For example, if you have this curve, you have made this curve, then you will need to look here. This is actually the center of the runner. So previously the center of the runner is in this location, but now you will need to translate it such that it lies at the center of the turbine, because the runner is rotating in this axis. So you will need to transfer your origin also in that line. So that is why in that case what happens is that Ri2, when you translate it, so you will translate it to the origin of the turbine, you will have to replace this plus sign to minus sign. And then this R and Z, they are actually representing the points where your runner is based on the coordinate system R comma Z. this is the example of how the coding can be done in MATLAB. So this is just an example. It is not the complete program. It is integrated with the other codes as well. So some of the values, they have already been determined. But this is a middle of the program, an example where it shows n axial, it is 100, and streamlines, it is 10. So you will get number of the points per streamlines n axial, and number of the streamlines is represented by and streamlines, which is 10 in this case. You can increase these values as well if you need. And similarly, first you will create zero matrix, because at the end you will get matrix, as I said you earlier, 100 times 10 matrix. So you will keep this value constant. Even if you cut some points away from your design, then you will need to redistribute it to 100 points or 10 points, because this matrix, if you for example change it, then the matrix manipulations are not possible. That's why when you cut some points, I will show you why you need to cut some points later on. But after doing some cutting, you might need to redistribute your point. So here there is this command as well, which is redistributing the points, because first you have this ellipse, and you have number of points in this ellipse. It doesn't matter, but what you need to do is that you will need to cut it into a semi-elliptical shape first of all. So in this case, here B is represented by 4 and A is represented by 1. You can also change it if you want, but then you will get only, if you cut this ellipse, you will only get one curve, and you will need to redistribute the points. So that redistribution is done in such a way that there are 100 points per streamlines all the time. So that is why this redistribute command is used. And then after this equation, as I showed you in the earlier slides, basically all these three equations are used. These are the three equations that are specially used. And what you get after that, you will have 10 number of the streamlines. So there are 10 streamlines in this case, and in each of the streamline there are 100 points. What happens is that by the time you reach the end of the streamlines, you will see that this kind of the curve are formed, which is very close to the shaft. So this creates two difficulties. One is that it lies very close to the shaft, and another difficulty is that there will be a very long blades in that case. So this means that you will have a curve which lies very close to the center. So your blade might go till here. So you don't want to do that. So you want to minimize the length of the blades, and that is why what we can do is that we can modify the trailing edge. So instead of going this far, we can trim some of the points away from our streamlines. So in this case, it has trimmed in this path. You can see the path of the trimming. And what does it look like after the trimming takes place? After the trimming, it will look something like this. What I did in this case was that I removed 1 point from the first streamline, I removed 2 points from the second streamline, 3 points from the fourth, 3 points from the third streamline, and so on. So you will remove most of the points when you reach the hub. But you can use your own formula as well, just that it has to be inside the loop, so that it is better to have some kind of the sequence. One important thing that you should not forget after trimming is that you should redistribute the points. So there should still be 100 points in the last streamline. So that is why what you need to do is that if you, for example, trimmed 10 points from your hub streamline, then there will be only 90 points left in the hub streamline. So this will create problems when you go further in the radial view. So at the end, you should have a matrix of 100 times 10, as I told you earlier. So that is why you will need to redistribute all these curves once again, so that the matrix size will remain as 100 times 10. Now, before moving further, we will discuss about the energy distribution. This is a curve which shows different values and the distribution starting from the inlet to the outlet of the runner. As you know that Cu is now 0 at the outlet, so Cu will be minimum. Cu at the inlet will be 1, so these values are relative to the inlet. So we can see that Cu is decreasing, and by the time it reaches the outlet, it will be completely 0. This means that U times Cu, because now our energy from our energy equations, Euler equations, we know that the energy can be represented by U times Cu. So this means that U times Cu will also be 0 by the time it reaches the outlet of the runner. U, what happens to U? U will also decrease, because you will have U, we know that U equals to omega times R. So as R is smaller in the case of the outlet, we will see that U will also decrease at the outlet. At the outlet, the Cm component will increase a bit, because we know that there is some acceleration required in order to drive the flow into the turbine. So that is why we can see that the Cm is slightly increased. And we can see that because of all these constraints, we can see that W, relative velocity, will be maximum at the outlet. So that is why we get the problem of erosion. We get the problem of cavitations at the outlet, because the relative velocities is very high at the outlet. And it is also written in this slide that for a high head turbine, it is desirable to utilize most of the energy at the beginning of the blade. So in this case, what we can see that by the time the turbine reaches about center of the streamline, then we can see that most of the energy has already been converted. So UCU is much less compared to what it was in the inlet. This kind of curve is desirable, because in the case of the Francis turbines runners, we can see that the blades, they are thicker at the inlet, and because of the small space at the outlet, the thickness has to be reduced. So that is why if we have a lot of conversion taking place at the outlet, then there might be the problem of fatigue and fracture failures as well. What we can do in this energy distribution is that we need to either choose the beta distribution, or we need to either choose the U times Cu distribution. So either you choose beta distribution to be linear, or you can also work with other shapes of the beta, and then you can get the values of the U times Cu based on this equation given here. So in this equation, what happens is that since you have now these streamlines already, so you got these streamlines from the previous code. Now what you can see is that in all these points, for example, if you are taking this point, or if you are taking this point, or if you are taking this point, in all of these points, U will be different, right? So U will be equal to omega times R. When omega is same, but the radius is different in all these points, you will get different values of U in all the points. And similarly, in the outlet also, I got this question last time. In the outlet, before we were only looking into this point, but now this point has different U, this point has different U, this point has different U. All the points will have a different value of the tangential speed. That is why we will have a beta distribution at the outlet as well. We will have a beta distribution throughout our streamlines. So there will be different values of all these components that we calculated, because our U will be different in all these points. CM in this curve can be now achieved as well, based on the fact that we have some acceleration, and then there will be the linear increase of the CM as it moves from inlet to outlet. So we can also get CM.